Hi, welcome back. Today's video we'll be looking at inductors. Before looking at inductors specifically, we need to understand their underlying principles and why this happens. For this, we'll be speaking about electricity and magnetism first of all. Let's get right into it. So if you've ever done the experiment of using iron filings and placing it around a magnet, you come to see the effects of a magnetic force. The lines around the magnet are otherwise known as flux lines. If you have not done it, I will simply draw out a quick visual representation. So this is our magnet, that's your north, south. So if you ever did sprinkle these iron filings around, you would see that the iron filings would arrange themselves in this type of configuration. So not without arrows, but that's just a visual demonstrator. So they've arranged themselves in that kind of configuration, and that's what we call the flux lines. And when electric current runs through a wire, it produces a weak magnetic field. And as the flux lines get farther away from the wire, it gets weaker. So if we had our wire here, you just have to visualize that there's a magnetic field going across it, and these flux lines are being generated. So that would be our wire, and that would be the magnetic field generated if we had a current running through it. What would happen if we were to wrap a wire around a magnet like so? This is a little drawing. This is our wire and our magnet. So magnet, wire. So these things are the wires. Well, nothing would happen, not until we move the wire or magnet. Well, this would happen. You get a current induced, and from this, if we moved it, so if we moved it down, a current will be induced, but however, it would flow in the opposite direction. And if we moved it up, and if we moved it up and down, we would get an alternating current, AC. So if we had this magnet going up and down through this stationary wire here, we get an alternating current. So as long as motion exists between the wire and magnet, current is induced within the wire. Now, the inductor. So the inductor is a passive component, and it's electrical symbol, or a circuit symbol I should say. It's drawn out like that. So if you see that in a schematic, you would know that is an inductor. And if we pass current through this inductor, we create a magnetic field around the wire. And so if we change the current by increasing it or decreasing it, the magnetic flux around the coil changes, and this induces a voltage across the inductor. And as we mentioned before, this voltage that we have just generated can cause a current to flow in the opposite direction of the main source of current. And this is otherwise known as self-inductance or inductance. So when I said coil of wire, I don't have an inductor with me, but if you did a quick Google search, but you would find some inductors are essentially just wrapped out the wire like so, and just have your leads in so you can plug into your breadboard and such. I'll try and include some images here. Inductance is used by the capital letter L, so that's inductance, and we measure it in henries. Measured in henries, which is H. As you might know by now, inductors oppose current change. But why is this so? So this is because if we draw out our circuit here, we have a resistor, power supply, when our power source is switched on, current starts to flow, and so it starts to flow. We're using conventional current here, so current starts to flow, and this induces a magnetic field around the coil of our inductor. So our magnetic field is being generated. And as the current starts to increase and ramp up, the strength of this magnetic field also increases. So we are pumping up the current, it's getting stronger and stronger, and because of this, magnetic field also gets stronger. And this change in magnetic field induces a back voltage. So there's being a voltage being induced, there's being induced here and here. The effect of the induced current continues and steadily reduces the strength of the growing magnetic field. And as the source of the current continues rising, the magnetic field around the inductor grows, but at a slower rate. So, like I mentioned before, if our current is increasing, this is growing, but it's growing slower and slower. The opposing current steadily continues to be induced. So remember, when there's a magnetic field around the coil, this induces a current going in the opposite direction. And because the steady current continues to be induced, this gets smaller and smaller. So this cycle repeats itself repeatedly until we reach a point where the current has reached the point of steady DC. It's going against it, and they'll reach a point where we just get a steady DC signal. And when this happens, the magnetic field no longer changes, and our inductor stops opposing the current. So this is no longer opposing, and it more or less just acts as a wire just flowing through. If all of this is confusing, then it is okay. Just keep in mind these points. 1. Inductors oppose current change. 2. When a DC supply is applied, our inductor acts as an open circuit, and this is due to current not flowing immediately. Remember, it needs to ramp up first until we reach that stable point. And so the entire voltage source drops across the inductor. And 3rd, our inductor will act as a short circuit in DC circuits once all the magnetic field has settled, and as mentioned before, the voltage will be 0 and the full DC current shall pass. But not least, inductive reactance. Similar to capacitance reactance, inductive reactance is the opposition of flow of AC current within an AC circuit. And the formula for this is XL. XL equals 2 pi FL. Our XL is inductive reactance, L is our inductance, F is our frequency, pi is pi, 3.14, and 2 is just 2. The inductor itself can be used for uses such as filters, transformers, or even energy storage. And this, along with many more useful functionalities, even using it to step up or step down voltages. A topology of which an inductor is used is the buck converter topology. That is all for inductors. Thank you for watching and hope you've learned something.